And now in this lecture we'll find out the area of the green shape. In the drawing we have square ABCD. You know that one side of this square ABCD is equals to 10 units in its length. Inside this square ABCD we have a quarter circle. This is a quarter circle. The center of the quarter circle is here at point O. And we have also a semicircle. This is a semicircle. And the center of this semicircle is here. So we'll define the center of this semicircle. This point is point O. BC is the diameter of this semicircle, and it is equal to 10 units, and therefore the radius must be equal to half of it. That is to say, the radius of this semicircle is equal to 10 over 2, that is 5. So the radius OB equals to 5 units in its length, and the radius OC also equals to 5 units in its length. AD is one side of square ABCD, therefore it is equal to 10. AD is also the radius of the quarter circle, so the radius of the quarter circle equals to 10, and the radius of the semicircle equals to 5. AB is also the radius of the quarter circle, that equals to 10 units in its length. In the next step, we will define the intersection point between the quarter circle and the semicircle. This point is point M. And we join points A and M together by a straight line. Point A is the center of the quarter circle. Point M is a point on the quarter circle itself. This is the quarter circle. Therefore, AM is the radius of the quarter circle. This equals to 10 units. Note that the radius of the quarter circle equals to 10. So AM equals to 10. In the next step, we join points O and M together by a straight line. Point O is the center. Point O is the center of the semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of the semicircle. This equals to 5. Here we can implement rule 1 because we have tangent AM, the tangent to this semicircle is point M. And we have the radius OM of the semicircle that is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And now your radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. Rule 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So this angle equals to 90 degrees according to rule 1. We know that ABCD is a square, and all the angles inside the square are right angles. So angle ABC is a right angle. In the next step, we join points A and O together by a straight line. By joining points A and O, we created the right triangle ABO. So we'll copy the right triangle ABO in a new page and We'll implement the Pythagoras theorem on this right triangle, triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AB of the right triangle ABO equals to 10 units in its length. Side BO equals to 5 units in its length. AO, the opponent AO is the missing side, so we find out the length of the opponent AO by implementing the Pythagoras theorem on this right triangle, triangle ABO. Here by PT is the evaluation for Pythagoras theorem. Okay, this is the right triangle ABO to the correct from the original drawing. In this right triangle ABO, AO square, that is the square of the hypotenuse, equals to AB square plus BO square. So write it down. AO square, that is the square of the hypotenuse, equals to AB square plus BO square. AO is the missing side, so leave it as it is. We have AO square is equals to AB square. AB is 10, therefore AB square is 10 squared, that is 100. Plus BO square. BO is 5, therefore BO square is 5 squared, that is 25. So in total, AO square equals to 100 plus 25, that is 125. So AO square equals to 125. We substitute 125 by 25 times 5. So AO square equals to 25 times 5. Here we take a root out of this equation and we get that the missing hypotenuse AO is equal to the square root of 25 times 5. The square root of 25 is 5, so inside the root we left only with 5. So in total we found out that the length of the hypotenuse AO is 5 times square root of 5. AO equals to 5 times square root of 5 units in its length. This is the hypotenuse AO is equals to 5 times square root of 5 units in its length. In the next step, we will prove that those two right triangles can go into each other according to side rule. So, write it down. We will prove that the right triangle ABO, this is the right triangle ABO, that it is congruent to the right triangle AOM according to side also. So why those two right triangles can go into each other? We prove that the right triangle ABO congruent to the right triangle AOM according to side rule. So why those two right triangles can go into each other? First of all, AB equals to AM, so both equal to 10, therefore they are equal to each other. So side AB in the right triangle ABO is equal to side AM of the right triangle AOM. Repeat again. side AB of the right triangle ABO equals to side AM of the right triangle AOM. They are both equal to 10 and therefore they are equal to each other. In addition, OB, side OB of the right triangle ABO is equal to side OM of the right triangle AOM. They are both equal to 5 and therefore they are equal to each other. So OB equals to OM equals to 5. Repeat again. Side OB, side OB of the right triangle ABO equals to side OM of the right triangle AOM. They are both equal to 5 and therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles, so we can write down that AO equals to itself is a common side that belongs to both triangles. AO equals to itself is a common side that belongs to both triangles. So we should prove that all the three sides of the right triangle ABO corresponding equal to all the three sides of this right triangle AOM, and therefore those two right triangles can go into each other according to side rule. So it's now we should follow that the right triangle ABO congruent, this is the sign of congruent, to the right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. Likewise, from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle AOM must be also equal to beta because they are equal to each other, according to the rule that I mentioned. So our task is to find out the area of this green shape, but first of all we have to find out the size of angle alpha and also the size of angle beta. So we focus on the right triangle ABO. In the right triangle ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. So write it down. In the right triangle ABO, sinus alpha equals to BO over AO. BO over AO. So sinus alpha equals to BO. BO is 5. AO. The hypotenuse AO equals to 5 times square root of 5. So in total, sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator and 5 in the denominator, so 5 will get cancelled. And we're left only with 1 over square root of 5. So sinus alpha equals to 1 over square root of 5. In terms of numbers, is equal to 0.4472 units. 1 over square root of 5 is 0.4472. So fundamentally, that sinus alpha equals to 0.4472. Our task is to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we'll operate on the result, that is 0.4472, the opposite function of sine, that is arc sine. In this way we get the value of alpha itself. So arc sine, that is the opposite function of sine of the result, that is 0.4472, equals to alpha. And use the computer in order to find out the value of arc sine. This arc sine is the opposite function of sinus. Arc sine of 0.4472 equals to alpha. And we get that arc sine of 0.4472 is equal to 26.565 degrees. Alpha equals to 26.565 degrees in its size. And what is the value of 2 alpha? 2 alpha equals to 53.13 degrees. 2 alpha equals to 53.13 degrees. In the right triangle ABO, the sum of the angles in a triangle equals to 180 degrees. So alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So in the right triangle ABO, or the right triangle AOB, the sum of the angles must be equal to 180 degrees. So which angles we have the right triangle AOB? We have alpha plus beta plus, this is the right angle. In total they must be equal to 180 degrees. Alpha plus beta plus 90 degrees, in total must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation and get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So here we subtract alpha from this equation and get that beta equals to 90 degrees minus alpha. Beta equals to 90 degrees minus alpha. And we already found out that alpha equals to 26.565 degrees. So beta equals to 90 degrees minus alpha, that is 26.565, and 90 degrees minus 26.565 is equal to 65.4 63.435 degrees. So angle beta equals to 63.435 degrees in its size. And what is the value of 2 beta? 2 beta equals to 2 times 65.435. That is actually 126.87 degrees. So in total we found out that 2 beta equals to 126.87 degrees and 2 alpha equals to 53.13 degrees. Our task is to find out the area of this green shape. So in the next step we will join points M and B together by a straight line. So if we focus on sector ABM, this is sector AMB or ABM. Sector AMB consists this segment MB. So we define segment MB. This is segment MB. We define segment MB as the lower segment, so we define segment MB as MLB. And this is the information for lower. So I'll copy sector A and B in a new page and we'll analyze this sector. So actually, this is sector ABM, that's the point from the original drawing. Sector ABM. The rounded sign above ABM is the sign for a sector. This is sector ABM. And we know that the big angle is alpha plus alpha, that is 2 alpha. The big angle is 2 alpha, and we already found out that 2 alpha equals to 53.13 degrees in its size. This is 2 alpha. And it equals to 53.15 degrees in its size. And we know that the area of any sector equals to pi r square. R is the radius of the circle that contains the sector. We define the radius as r, so it is pi r square times the angle between the legs of the sector, that is 53.15 degrees over 360 degrees. So the area of this sector equals to pi r square times 53.15 degrees over 360 degrees. R is the radius of the quarter circle, that is 10. R equals to 10, therefore r squared is 10 squared, it is 100. So pi r squared is 100 pi times 53.15 over 360 degrees. So in total, the value of this expression, 100 pi times 53.15 over 360 degrees, is actually equals to 27.678 square units in its size. So if you found out that the area of this sector ABM is equal to 27.678 square units in its size. This is segment BLM. Segment BLM. Again, the green shape is segment BLM. Actually, our task is to find out the area of segment BLM. So first of all, we find out the area of the lower segment BLM. This is the lower segment BLM. We have also the upper segment. We define the upper segment as segment BUM. BU is abbreviation for upper. And the area of the upper segment BUM plus the area of the lower segment BUM will be equal to the area of the green shape. So we found out that the area of sector ABM is equal to 27.678 square units in its size. The area of the sector ABM the area of sector ABM minus the area of triangle ABM equals to the area of segment BLM. Again, the area of segment BLM, this is the area that we are looking for in this question. This is actually, we have to add to segment BLM, the area of segment BLM, to the area of the upper segment BUM. This will be the area of the green shape. So first of all, we find out the area of the lower segment BLM. The area of the lower segment BLM will be equal to the area of the big sector ABM we already found out that the area of the big sector ABM equals to 27.678 square units in size. And from the area of sector ABM, we have to subtract the area of this triangle ABM minus the area of triangle ABM. This the area of sector BLM. We already found out that the area of this sector ABM equals to 27.678 degrees in its size. We have to subtract from the area of sector ABM the area of this triangle ABM. We know that AB equals to AM, AB equals to AM equals to 10. Side AB equals to 10, side AM equals to 10, and the angle here is 53.15 degrees. The area of this triangle equals to AB times AM, AB times AM, AB times AM, times sinus 53.15 over 2. Actually, I calculated the area of this triangle ABM, according to the formula that if you have triangle ABC, that could be any triangle. This is triangle ABC. That could be any triangle. The left of side AB is A. The left of side AC. Side AC equals to B units in its length. And this angle equals to theta. Then the area of this triangle ABC equals to A times B times sinus theta over 2. Read again. The area of this triangle ABC, that could be any triangle, equals to A times B times sinus theta over 2. So according to this formula, the area of this triangle ABM equals to AB times AM times sinus 53.13 degrees in its size over 2. AB is 10, AM is also 10, times sinus 53.15, sinus 53.15 is equal to 0.8 divided by 2. So the area of this triangle ABM equals to 10 times 10 is 100, and 100 over 2 is 50. 50 times 8.5 is 40. So in total, we found out that the area of this triangle ABM is equal to 40 square meters in its size. Actually, here we have 100 pi over 360 degrees is equal to 46.364. Actually, the area of this segment ABM is equal to 46.3646 square meters in its size. Repeat again. The area of this sector ABM is equal to 46.3646 square units in its size. The area of sector ABM is equal to 46 0.3646 square units in its size. And we just right now found out that the area of this triangle ABM is equal to 40 square units in its size. So the area of sector ABM is equal to 46.3641 square units in its size, minus the area of triangle ABM, triangle ABM, then equals to 40 square units in its size. So the area of sector, the area of segment BLM actually it is very easy to see that the area of segment BLM equals to the area of sector BLM, the area of sector OBM minus the area of triangle ABM. This is actually 46.3641 minus 40. This is actually 6.3641 square units in its size. And again, we should find out that the area of the lower segment BLM is equal to 6.3641 square units in its size. The area of this sector BLM is equal to 6.3641 square units in its size. So, the next step, we find out the area of the upper segment BUM is of course equals to the area of this sector BOM minus the area of triangle BOM. And again, the area of the upper segment BUM equals to the area of sector BOM minus the area of triangle BOM. So, the area of the upper segment BUM is equal to the area of sector BOM this is sector BOM minus the area of triangle BOM. Actually, it is very easy to see that the area of sector BUM, this sector, the area of this segment BUM, the area of this segment BUM equals to the area of sector, this sector BOM minus the area of triangle BOM. But again, it is very easy to see that if you subtract the area of this triangle BOM from the area of this sector BOM, you will get the area of this segment BUM. It's very easy to see it from the drawing. The area of segment BUM equals to the area of sector BOM minus the area of triangle BOM. So we have to find out the area of sector BOM. We know that BO equals to 5. This is the radius of the semicircle. OM also equals to 5. Let's see here that BO equals to 5. OM also equals to 5. And we have here triangle BOM. BO equals to 5. This is actually an isosceles triangle. OM also equals to 5. And the angle between the legs of the segment BOM is 2 beta. We already found out that 2 beta equals to 126.87 degrees in its size. 2 beta equals to 126.87 degrees in its size. So the area of this sector BOM equals to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 over 360 degrees. R is 5, therefore r square is 5 square, that is 25. So pi r square is 25 pi times 126.87 over 360 degrees. That is the area of this sector BOM. And the value of this expression, 25 pi times 126.87 over 360 degrees. In total, it is equal to 27.678 square units in size. Repeat again. The area of this sector, in total, it is equal to 27.678 degrees in its size. Again, the area of this sector BOM equals to 27.678 square units in its size minus the area of this triangle BOM. According to the formula that I presented to you, the area of this triangle must be equal to 5 times 5, this is 25, times sinus, this again equals to 186.87 degrees over 2. 5 times 5 is 25, and sinus 126.87 is equal to 0.8 over 2. 25 over 2 is 12.5. 12.5 times 0.8 is 10. So in total, we found out that the area of this triangle BOM, this isosceles triangle BOM, equals to 10 square units in its size. And the area of the sector BOM, that is 27.68 minus 10. 27.678 minus 10 is 17.67 square units in its size. So the area of the upper segment BUM equals to 17.678. is again the area of the upper segment BUM equals to 17.678 square units in size, plus the area of the lower sector, the area of the lower segment. We already found out that the area of the lower segment equals to 6.3646 square units in size. And the area of the green shape in total equals to the area of the upper segment plus the area of the lower segment. This is actually 16.678 plus 6.3646 square units in. So in total 17.678 plus 6.3646 is equal to 24.0426 square units in size. This is the answer to the question. Please again, we should find out that the area that we are looking for in this question, that is the area of this green shape, it is actually equals to the area of the upper segment BUM plus the area of the lower segment BLM. The area of the upper segment BUM equals to 17.678 plus the area of the lower segment BLM. This equals to 6.3646 square units in size, and in total it is equal to 24.0426 square units in size. That is the answer to the question. So, in the next step, I'll summarize the lecture. Our task in this lecture is to find out the area of this green shape. So, in the drawing, we have square ABCD. We know that one side of this square ABCD is equal to 10 units in its length. Inside this square, we have this quarter circle and this semicircle. We know that BC is also, it is not only the side of the square, but it is also the diameter of the semicircle. So the diameter of the semicircle BC is 10, therefore the radius OB is 5, the radius OC is also 5, and inside this square ABCD we have this quarter circle. Point A is the center of the quarter circle. Point B is the point on the quarter circle itself. Therefore, AB is the radius of the quarter circle. That is 10. So, conclusion, we found out that the radius of the quarter circle is equal to 10 units in its length, and the radius of the semicircle is 5. AD is also the radius of the quarter circle, that is 10 units. So in the next step, we join points A and M together by a straight line. Again, point A is the center of the quarter circle, point M is the point of the circle itself, therefore AM is the radius of the quarter circle, that is 10. We join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is 5. AM is the tangent to the semicircle at point M. OM is the radius of the semicircle, that is 5. So here we can implement rule 1, because we have the radius OM, the radius OM of the semicircle, that is equal to 5, is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius that is drawn to the point of tendency, then according to rule 1, tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. The next step, we join points A and O together by a straight line. We know that all the angles inside the square are right angles, and therefore This is angle ABC, that is a right angle, because it is 1 out of 4 angles of square ABCD, therefore it is a right angle. So in the next step, we implemented the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABO, AO square equals to AB square plus BO square. AO is the missing side, so it is. And it is equals to AB square plus BO square. AB is 10, therefore AB square is 10 square, that is 100, plus BO square. BO is 5, therefore BO square is 5 square, that is 25. So in total, we should find out that AO square equals to 10 square, that is 100, plus 5 square, that is 25. So AO square equals to 100 plus 25, that is 125. If we take out all this from the equation, we get that AO equals to the square root of 125. It's actually 5 times square root of 5. Okay, so AO equals to 5 times square root of 5 units, and it's 9. In the next step, actually focus on the right triangle ABO. On the right triangle ABO, sinus alpha equals to BO over AO. So sinus alpha equals to 5 over 5 times square root of 5. Here we have sinus alpha equals to 5 over 5 times square root of 5. This is 1 over square root of 5. And therefore alpha itself equals to arc cosine of 1 over square root of 5. This actually equals to 26.565 degrees in its size. And therefore 2 alpha equals to 2 times 26.565, this is 53.1 degrees. So 2 alpha equals to 53.13 degrees in its size. Likewise, actually, you know that in any triangle, the sum of the angles must be equal to 180 degrees. So in the right triangle ABO, alpha plus beta plus 90 degrees, in total they must be equal to 180 degrees. So we subtracted 90 degrees from the equation, and we found out actually that alpha plus beta equals to 90 degrees. So if alpha plus beta equals to 90 degrees, it means that alpha equals to 90 degrees minus beta, but alpha equals to 26.565, therefore beta equals to 90 degrees minus alpha, that is 90 degrees minus 26.565, this actually equals to 63.435 degrees. Therefore 2 beta equals to 2 times 63.345, this is actually 126.87 degrees. So 2 beta equals to 126.87 degrees in its size, and 2 alpha equals to 53.13 degrees in its size. And our task is to find out the area of this green shape. So first of all, we join points M and B together by a straight line. By joining points M and B, we're going to enter there 2 segments. We have the upper segment MUB, and we have the lower segment MLB. So first of all, we found out the area of the lower segment MLB. What is the area of this lower segment MLB? The area of the lower segment MLB equals to the area of the big sector AMB minus the area of this triangle AMB. Again, the area of the segment, the lower segment MLB equals to the area of the sector AMB minus the area of this triangle AMB. And again, the area of the lower segment MLB equals to the area of the big sector M, A and B minus the area of triangle A and B. The area of sector A and B, actually the area of any sector equals to the area of the circle that contains the sector times the angle between the legs of the sector, that is 53.15 over 360 degrees. So in total we should find out that the area of sector A and B equals to 46.3646 square units in its size minus the area of this triangle A and B. The area of this triangle A and B equals to AM times AB times sinus 53.15 over 2. So in total we found out that AM is 10, AB is also 10, so it is 10 times 10 is 100 times sinus 53.15 over 2. Sinus 53.15 is 0.8, so 10 times 10 is 100, and 100 over 2 is 50. 50 times 50 times 0.8 is 40. So if you found out that the area of this triangle MBA is equal to 40 square units in its size minus the area of sector A and B, that is 46.3646. So 46.3646, that is the area of this sector A and B minus the area of this triangle A and B, that is 40. In total it is 6.3646 square units in its size. So in total we should know that the area of this segment BLM is equal to 6.3646 degrees in its size. Repeat again, the area of this segment BLM is equal to 6.3646 square units in its size. And we have to add to the area of this segment BLM the area of the upper segment BUM. What is the area of the upper segment BUM? The area of the upper segment BUM, before that I put on what we did until now. The area of this segment BLM equals to the area of the sector BUM, that is 46.3641 minus the area of this triangle BOM, that is 40. So 46.3641 minus 40, it is the area of this sector MLM, MBLM, is actually 6.3646 squares in its size. And we have to add to the area of this lower sector BLM the area of this upper segment BUM. So what is the area of this upper segment BUM? The area of the upper segment BUM equals to the area of sector BOM, the area of this sector BOM, minus the area of this triangle BOM. Again, the area of sector BOM minus the area of this triangle BOM equals to the area of the upper segment BUM. And again, the area of sector BMO minus the area of triangle BMO equals to the area of segment BUM. So the area of sector BMO equals to the area of the circle that contains the sector, that is actually pi r square. R is 5, therefore r square is 5 squared, that is 25. So in total pi r square is 25 pi times the angle between the legs of the sector, that is actually 53.15 divided by 360 degrees. Actually, the angle between the legs of the sector is 126.87 degrees. So it is pi r square. R is 5, so r square is 5 squared, that is 25 over 2. 25 over 2 times sinus 186.87 degrees. This is actually 0.8. So in total, the area of this sector BOM equals to 25 over 2 times 0.8. 25 over 2 is 12.5 times 0.8, that is 10. So actually found out that the area of this triangle BOM equals to 10 square units in its size, minus the area of sector BOM. The area of sector BOM equals to pi r square. R is 5, so pi r square is 25 pi, times the angle between the legs of the sector, that is 126.87, divided by 360 degrees. So in total we should find out that the area of this sector BOM equals to 27.678 degrees in size, minus the area of this triangle BOM, that is 10. So 27.678 minus 10 is 17.67 square units in its size. So in total we should find out that the area of the upper segment BOM equals to 17.67 degrees in its size. And the area of the green shape in total equals to the area of the upper segment BUM, that is 17.678 degrees in size, minus the area of the lower segment BLM, that is 6.3646. So the area of the upper segment BUM, that is 17.678, minus the area of the lower segment BLM, that is 6.3646. In total, it is equals to 24.0426 square units in size. So in total, if you found out that the area that we are looking for this question, that is the area of this green shape, is equal to 24.0426 square units in size. Okay, thank you very much.